Okay, so welcome to the COVID-19 version of Calc 3. It occurred to me after I posted the video the other day that I probably could have added this in as a tag. So this is going to be a short video. I just have to adjust my display because I forgot to do that. Okay, there we go. I want to talk about tangent planes. So, we talked about the first partials and what it means for a function of two variables to be continuous. All right, so if f has continuous first partials, all right, then f is continuous, right? So if f has continuous first partials, then we can write an equation for a tangent plane to the surface at a point. All right, so f has to be continuous at that point. It doesn't have to be continuous in general. It just has to be continuous at the point that we're writing the tangent plane for. All right, so f has continuous first partials, right? So f has okay, not getting off to a good start here. Hang on. Continuous first partials then the tangent plane then the tangent plane. I should point out that I'm recording this at 7:30 in the morning, so that could also be why I'm a little off. The tangent plane to the surface and remember our surfaces have the form z equals f of xy at a point. All right, so at the point x0, y0, z0 is given by this formula, z minus z0 equals fx. Remember, fx is the first partial with respect to x, x0, y0, x minus x0 plus fy, the first partial with respect to y, x0, y0, y minus y0. All right, so you should recognize the general formula for a plane at this point. All right, so fx and fy are acting as our vector for the plane. Okay. So if I have, let's see, what do I have here? I have f of xy equals 2x squared plus y squared, yes. All right, so I have an upward facing elliptical paraboloid, I believe. All right, you can go to GeoGebra and graph that if you want. At the point 1, 1, 3. All right, and what I want to do is write the equation for the tangent plane. Now, of course, I don't have this problem done in my notes, and I didn't look ahead. As usual, you should be used to this by now. So we're going to do this together. So find the partial with respect to x and the partial with respect to y. All right, I'll do it here. You guys do it at home. All right, fx. Again, with respect to x, remember, this is what we're taking the derivative of, so that's going to be 4x. And then with respect to x, y is a constant, so that's 0. fy, xy. All right, with respect to y now, this term is a constant. So this is what we're taking the derivative of. So 2y. All right, now we need those evaluated at the point 1, 1, 3. So just remember, be careful when you do this. First is x, then is y. That's what we're plugging in. The 3 is just the value of the function. All right, so that actually does not come into play until we write the equation for the plane. All right, so fx at 1, 1. All right, I plug 1 in for x and I get 4. Fy of 1, 1. And I plug 1 in for y and I get 2. All right, so I go back up here. This is the form for the equation of the plane. So I'm going to have z minus z0, which is 3. Whoop, that is not what I wanted. That was habit from vectors. Hang on. Equals fx x0 y0. So that is 4 x minus x0, which is 1, plus fy x0 y0, so that is 2, y minus y0 rather, which is 1. All right, so there's my plane. If I want to, I can do the algebra to put this into the form that I'm used to seeing a plane in, which I guess I'll do. Why not? It's going to be a short video. I might as well waste a little bit of time. All right, so 4x minus 4 plus, of course, this is where I'm most likely to make a mistake. I'll be careful. All right, so we get 4x plus 2y. All right, so I'm going to bring the z over, so minus z equals, so I need to bring both of these over to the other side. So that's minus 6. So when I bring it over here, that becomes plus 3. All right, so there is the equation of the plane that you are used to seeing. Okay. All right, now, back in Calc 1, when you did the tangent line, one of the things that you hopefully went over, I know I do it when I teach Calc 1, is estimations, the differential. Okay. Now we can use the tangent plane in a way that is similar to using the tangent line in R2 for a linear approximation or a differential. So before I do this, I want to, let me switch over to the textbook here for a minute because I want to point to a definition. All right, so we have a definition right here, definition 7. All right, and it basically describes differentiability and what the differential is going to look like. All right, so if z equals f of xy, so we have our surface, all right, then f is differentiable at ab if delta z can be expressed in this form right here. All right, so this is the differential, right? The differential of z, right? Fx delta x plus fy delta y plus the epsilons on the deltas, okay? All right, and we want epsilon 1 and epsilon 2 to go to 0 as delta x delta y goes to 0, 0. All right, so what this definition does is it gives us a theorem, and I'm going to put the theorem on my whiteboard. Hang on. This is tricky because I have to only have one monitor on in order for me to write, and I can't see my switcher, so I'm hoping that's switched. I'll watch the video before I post it. Okay, so we get a theorem from this, which says, I'll read it, then I'll write it, all right? If the partials, fx and fy, exist near AB and are continuous, all right, then are continuous at AB, then f is differentiable at AB. All right, so let's do this here. If the partials, first partials, I could just say first partials, but fx and fy are exist, right? They have to exist first, I guess. Exist near AB. Right? And they're continuous. All right, and they're continuous at AB. All right, then f is differentiable at AB. All right, so if we just kind of break this down just a little bit, right? We already know if the partials exist and are continuous, then the function is differentiable. When we're looking at a specific point, we need to basically think about piecewise functions in R2, right? It's possible to have a function where the limits exist at a particular point, but the function is not equal to the point at that is not equal to the same value as the limit at that point. You have basically a hole with a removed point. That's what we're trying to eliminate here. All right, is a hole with a removed point. So we're requiring that the partials exist near AB. All right, that is that the limits approach, that they are continuous at AB. So that means the value of the function exists and is the same as the limit. All right, then we can say that f is differentiable at AB. All right, we need differentiability at AB in order to write the differential. Okay, in order to do an approximation. All right, the approximation is not going to exist if the function doesn't exist at the point that we're approximating. All right, or if the value of the function is removed as a whole and a removed point from the function. All right, so if I have a function here, all right, so let's do this. F of xy, we'll get some more practice doing partial derivatives too. All right, f of xy is e to the xy plus, nope, wait, time out. Looking too far down on my notes. Try that again. Again, the 30-second rule still applies here. X e to the xy. That's what I want for the function. All right, so we need the partials. We have to check those first. Fx, xy. All right, now we're doing this with respect to x, and because I have an x here and I have an x here, all right, that's a product, which means I have to use the product rule. All right, so in order to do that, okay, I did it backwards here. That's okay. All right, so if we do the derivative of x, right, the derivative of the first times the second, I'm going to get e to the xy plus the first times the derivative of the second. And so that's going to be x e to the xy. Leave yourself a little bit of room here, right? E to the xy, because that's an e, times the derivative of xy with respect to y. I'm sorry, with respect to x is going to give me a y there. Fy xy, okay, is not a product, right? Because we're doing this with respect to y. Right, so since we're doing this with respect to y, we're going to get x, and then the derivative of e to the xy, which again is going to be e to the xy, times the derivative of xy with respect to y, which means x is a constant, so that's just going to throw another x out front. All right, so there are the first partials. Now, remember, for the function to be continuous, we need the first partials to be the same. Now, just because the first partials aren't the same doesn't mean the function is not continuous. Remember, that's a one-way statement. So my first partials are not the same, but I don't care if the function is continuous everywhere. I only care that it's continuous at a specific point. All right, so let's take a look at this. We want to see if this is differentiable at, and the point I'm looking at is 1, 0. Okay. So again, I don't care if the first partials are equal everywhere. I only care that they're equal at 1, 0. All right. So fx, okay. I'm usually pretty good first thing in the morning. Fx 1, 0 is, all right, so e to the 1 times 0. So that's e to the 0, so that's 1. 1, 0, so that's 1, that's 0, so that whole term is 0. So that's equal to 1. Fy 1, 0. All right, so x is 1. 1, 0 again is 0 up there, so that's 1, so that's 1, so that's 1. All right, so my first partials are equal at 1, 0. All right, so at 1, 0, fx is equal to fy. All right. All right. So that means they're continuous. So fx, oh, that's an x, fx and fy are continuous at 1, 0. Therefore, I showed you that little thing for therefore, right? Therefore, f is differentiable. At 1, 0. Remember, everything is at this point here, okay? At 1, 0. So what that means is I can calculate the differential. So I'm going to go back to, hang on a second, I need more room. I gotta admit, this is easier than erasing the board every time. Okay. All right, so now if I want to write the differentiable, an approximation at that point, all right, so I'm going to use my tangent plane, all right, and we're going to go this way with it, all right? This is what it's going to look like. F of xy, all right, which is our z. Usually we'd say z minus z0, but what I'm going to do is, because we're approximating this, I'm going to move that z0 over to the other side. So it's going to be f of ab, I'm going to write it out in general first, plus fx of ab times x minus a plus fy of ab times y minus b. All right, and that's how you, when you're using the differential as an approximation, that's how you do it. Okay, so my linear approximation, what's going on with my pen here? I might have to change the battery. My linear approximation at 1, 0, all right, is going to be approximately equal to f of 1, 0. I'll go this a step at a time, right? F of 1, 0 plus fx 1, 0 times x minus 1 plus fy of 1, 0 at y minus 0 there. Okay. All right, so now I can just drop everything in. So this is going to be equal to f of 1, 0. All right, so if I go back to my function, which is up here somewhere, hang on. So if I go back to my function, there's my function right here. So at 1, 0, all right, if I put 1 in here, 1 in there, 0 in there, that's e to the 0. That's 1. So the whole thing, once again, is equal to 1. All right, so that's going to be 1 plus... darn it, I went too far. Hang on. I believe... Yeah, there they are. Okay. Okay, fx10 is right there. That is 1. Fy of 10 is also 1. That was the whole point. All right, so our linear approximation becomes 1. When I distribute that, that's going to be a minus 1. So that's going to leave me with x plus y. All right, so we can approximate the function. What this is saying is we can approximate the function f of xy. I should make that, if I'm going to do that, I'm going to turn that back to an approximately equal to, near the point 1, 1, by using the plane x plus y. Z equals x plus y. Okay, so we get a general differential form. I guess I'll do it over here. We get a general differential form here as dz, regular d, not curly d, equals fx dx plus fy dy, dy for a linear approximation. Okay. All right, so I'm going to get this video posted, and I will see you all later this evening.